Hello friends, what's up? Welcome in the world of Maths by Amiya. First of all, I want to clear one thing. With the help of cyclicity, we do not find remainder, but we reduce power. If we have a number a raised to power b divided by c and we need to find remainder, then with the help of cyclicity, we just reduce the power and get remainder according to the basic remainder concept. First thing we should know is what is remainder. Remainder is nothing but the extra amount left when we divide a number. For example, when 17 divided by 15, what would be remainder? We divide 17 with the help of 15 only one times, that is nothing but 1, and the 2 out of 15. This out of is the extra. Means when we convert a fraction into a mixed fraction, the numerator part is the remainder, this integral part is the quotient. Second thing we should know the types of divisor. There are mainly three types of divisor. One is prime, we know. Second one is composite number, but prime raised to power something. For example, prime is nothing but 2, 3, 5, 7 and so on. The prime raised to power something is 2 raised to power 3, 5 raised to power something. Means these are the composite numbers, but in the prime factorization we have only one prime in their base. And the last one is composite numbers with the bundle of more than one primes with some powers, maybe some power may not be. For example, 6 is a 2 into 3, we have 2 primes in the prime factorization. For example, 30, we have 3 primes in the prime factorization, or 12, that is 2 squared into 3. So we have mainly three types of divisors when we talk about cyclicity. And in the primes, we again segregate. This is the even divisor. This category is 2 or 2 raised to power something, because this is an even, and rest. Rest means others primes or their power. So before starting cyclicity, you should know the types of divisor, that is either 2 or power of 2 is the one set of prime, others prime or rest power of that prime, and the rest is the composite numbers. You can think, why not 1? When any number divided by 1, remainder is always 0. 1 is a factor of all numbers, so we exclude 1 from the types of divisor. To start the concept of remainder, first of all we should know the relation between divisor and dividend. There are two types of relation between divisor and dividend. One is when both are co-prime, there is nothing common, or say HCF is 1. Another one is non-co-prime, when their HCF are not 1. HCF can be anything. So we can say we would get co-prime as a remainder with divisor if divisor and dividends are co-prime, or we will get non-co-prime remainder if our divisor and dividend are not co-prime. This is the most important thing to start our concept of cyclicity. Co-prime divisor and dividend gives remainder co-prime. Non-co-prime divisor and dividends gives non-co-prime remainder. Consider as 5 and dividend as any number which is co-prime of 5. We know the co-prime of 5 less than 5s are nothing but 1, 2, 3, 4. Can we say there are the 4 co-primes less than 5? Why so? If you take any prime, less than that prime, all numbers should be co-prime, because there is nothing common between prime and the other numbers. Take example of 7. All the number less than 7, say 1, 2, 3, 4, 5, 6 are co-prime of 7. So these values 1, 2, 3, 4, 5 could be remainder when 7 divides another number. So we have 6 options when 7 divides another number. We could have less than 6 options too, but the maximum number of options when 7 divides another number which is co-prime of 7 is 6. Same with 5. When 5 divides another number, the maximum option we could have is 4 when 5 divides another co-prime. Now check how. Take divisor as 5. So our remainder options are 1, 2, 3, 4 if 5 divides another number which is co-prime. If we take 1 as a remainder, say 6 divided by 5, what is remainder? The remainder is 1. What is 6 square divided by 5? Remainder is again 1. So when your first remainder is 1, the next consecutive power remainder is always 1. So we generally ignore when we find the cyclicity with the 1. We also ignore when we find 4, that is nothing but minus 1 in the case of 5. 4 divided by 5, remainder is minus 1. 4 square divided by 5, that is 16, remainder is plus 1. So we are not using all the options, but when we take 2 as a number, so what is the value? 2 raised to power 5, remainder is 2. 2 square raised divided by 5, remainder is 4. 2 cube, that is nothing but 8 divided by 5, remainder is 3. 2 4 divided by 5, that is nothing but 16, remainder is 1. If we go for the 2 5 divided by 5, remainder is 2. So if you check, I take a value 2 which is neither 1 nor minus 1 for the 5, then we'll use all the values. That is, for the 2 we use 2, for the 2 square we have 4, for the 2 cube we have 3, for the 2 raised to power 1 we have 4. So we used all the co-primes less than 5 if we take 2. So whenever we take neither 1 nor minus 1 and the next value, we use all the co-prime values. So we can say if divisor is prime, we will use all the co-primes less than 5. And you should know, if your divisor is prime, all options of remainder is nothing but prime minus 1. If divisor is 5, the other options are 4. If divisor is 7, the other options are 6. And these options are known as cyclicity. You can also say this is nothing but the Euler or the phi. But according to the cyclicity is nothing but cyclicity is the option available for the divisor. So we can say cyclicity is nothing but options available to get different remainders when divided by a number. So when a prime number divides another number which is co-prime of that prime, then the other options are nothing but prime minus 1. All the options, say 11, we have all options 1 to 10 which are co-prime of 11. Why only 1 to 10? Because remainder is always less than the divisor and should be greater than or equal to 0. I am not taking 0. Why so? Because when we take 0, these two becomes non-co-prime. The first thing you should know, when we have prime number, the cyclicity is prime minus 1, which is nothing but the Euler. Do not confuse cyclicity with the Euler. Cyclicity is the number of options available for the remainder, and the Euler is number of co-primes. In the case of prime, both are the same. So we are working in the condition when we have divisor and dividend. Both are co-prime, so our remainder should be also a co-prime of divisor. The first one is, if your divisor is prime, then the cyclicity is nothing but the prime minus 1. I hope it is clear. When our number is composite, how do we find the cyclicity? This is the most important thing. And what is the meaning of cyclicity? When our number is composite, then the composite divides into prime raised to power some power or prime bundles, means product of two different primes in the base in the prime factorization. Prime raised to power some bundle is nothing but 2 raised to power some bundle or other primes raised to power some power. Prime power is nothing but 2 raised to power and rest prime raised to power 2 raised 5 raised 2 raised to power m, 5 raised to power m, 7 raised to power m. Why I am taking 2 as a different case? Because 2 is the exceptional prime, which is nothing but even. And also the part of our base is 10, so 2 into 5, and 2 is the exception, so I am taking 2 as a different case and the rest prime as a different case. Now work on the rest prime first, then work on a 2, then we work on a prime into prime bundle. We know For the 5, we are 4 different co-primes. All the cyclicity of 5 is 4 because we have 4 co-primes less than 5, or the say 4 options available for the remainder. If for the 5 we have 4, what is the value for the 5 square? We can use the unitary method if we have same type of primes. For the 5, cyclicity is 4. Then what is the cyclicity for the 5 square? We can use unitary method if we have same type of prime. For the 5, we have 4. For the 1, we should have 4 by 5. For the 5 square, we have 5 square multiplication. That is nothing but 20. Same case, for the 7, our number of options available for the remainder is 6, or you can just say cyclicity is 6. For the 7 cube, the cyclicity should be 6 by 7, because for the 7 we have 6. For the 1, we should have 6 by 7 by the unitary method, and for the 7 cube, that is nothing but this. So by solving this, we have 6 into 7 square options available when number divided by 7 cube, and the divisor and dividends are co-prime. So we can generate a formula of cyclicity which is same as the Euler. In the case of prime, if we have prime, then the cyclicity is p into 1 minus 1 by p, which is nothing but p minus 1. If you have p raised to power n, then the cyclicity is p raised to power n into 1 minus 1 by p. Why I am doing 1 minus p, we'll see in the different concept video when we discuss Euler. But this is only applicable for the rest of the prime. P should not be equal to 2. We check everything. For the 7, we have 6. For the 7 cube, we have 6 into 7 square. But when we have 2 raised to power 4, we are not going to use 2 raised to power 4 into 1 minus 1 by 2. According to cyclicity, this is a wrong process. This is the perfect Euler of 2 raised to power 4 is 2 cube is nothing but the 8. But it is not the cyclicity. Now we have to check cyclicity. 2 raised to power n. What I said about the cyclicity? Cyclicity is the remainder options for any divisor if we have co-primes, dividend. For say 2 raised to power 3, that is nothing but 8. If the divisor is the co-prime of dividend, then we will get the options as a co-prime. The co-prime of 8 are nothing but all the options available for the odd number 1, 3, 5, 7. For the 8, there are the 4 co-primes, or you can say the Euler of 8 is 4, but 4 is not the cyclicity of 8. Why? In the starting of the video, we avoid taking 1 and 7 because 1 will give always 1, 7 is nothing but minus 1, so we'll give next 1 and so on. So say take 3. 3 raised to power 1 divided by 8 is nothing but 3. 3 square divided by 8, that is 9, nothing but 1. So if we took 3, we have only utilized 3 and 1. Take 5. 5 divided by 8, remainder is 5. 5 square divided by 8, remainder is nothing but 25 divided by 8 is 1. So even if I took 5, the next is 1. I am not using the complete set of the 1, 3, 5, 7 as co-primes. We have co-primes as a 4, but I am only using 5 and 2, means we are getting only 2 options. So when you have 4 co-primes, you are getting 2 options, means we are just getting half of the options, we are not utilizing the other half. Say our divisor as a 16 and dividend is the one of the co-prime of 16. So co-prime of 16 is all odd numbers less than 16, which are nothing but 1, 3, 5, 7, 9, 11, 13 and 15. If you count all, that is nothing but 8. Or by the Eulers, we can find the 8 is the Euler of 16, or the number of co-prime less than 16. But we work in a cyclicity. We are not using the 8 as a value to solve quotient. We are not going to take 1, take 3. Since we just jumped 1, the gap is of 2. If you remember, the gap is of 2. So we are missing half of the primes. If you check gap between 2 consecutive co-primes, the gap is of 2. So we are missing half of the co-primes always. The cyclicity should be 8, but the gap between 2 consecutive co-primes is 2. So we can say the cyclicity will be 8 by 2 is nothing but 4. So the cyclicity of 16 is 4. Work on the values 3, that is 3 raised to power 116 is 3. We work 3. 3 square divided by 16 is nothing but 9. So we work with the 9. We used 3. We used 9. 3 cube divided by 16, that is 27 divided by 16. Then the remainder is 11. We used 11. 3 raised to power 4 divided by 16, that is nothing but 81 divided by 16 is 1. We used 1. When we get remainder as a 1 for the co-prime, the next is nothing but the repetition, that is 3 again, 9 again, 11 again, 1 again, and so on. So when we have 2 raised to power something, the gap between the conjugative co-primes are nothing but 2, so we have to divide this value by the 2. So to get cyclicity, we need to divide Euler's for the co-primes divided by 2. Why I am saying 2, 2, 2? Take example of 11. 11 is a prime. The co-primes are 1, 2, 3 till 10. There is gap of only 1. So we just work the co-prime is nothing but the cyclicity also. But in the case of 2 raised to power n, our cyclicity is 2 raised to power n into 1 minus 1 by 2 divided by 2, which in turn becomes 2 raised to power n minus 2. Now, how do we find cyclicity for the composite numbers, which is in the bundle of 2 primes? Before this, you should know one language of the maths. If we use AND in number system, it means LCM we are using. If we want 2 and 3 in number system, so we are saying we are looking for 6, the LCM. If we want 6 and 8, it means we are looking for 24. If you want 2 and 3 properties, you should know it's all about 6. If someone is talking about 6 and 8 properties, he is talking about 24. In number system, AND is nothing but LCM. In permutation and combination, AND is nothing but multiplication. So we can say whenever we have multiplying in our factor, we use LCM when we working in a number system. So if I say what is the cyclicity of 30, so first of all, 30 is not a number in the term of number system. We need to factorize. This is the bundle of 2, 3 and 5. When you have any composite number except 2 raised to power n or any prime raised to power n, we need to factorize. If we have more than one primes in a base, so we find the individual cyclicity. The cyclicity of prime is just 1 less than, so the cyclicity of 2 is 1, prime is 1 less than is 2, prime is 1 less than is 4. And multiplication is nothing but and is what? LCM. How? 2 says we repeat after 1, 3 says we repeat after 2, 5 says we repeat after 4. So when we have to satisfy 2, 3, 5 means when we have to satisfy the repetition of 1, 2, 4, we can say, okay Baba, repeat after 4, which is nothing but the LCM. Take another example. If someone asks what is the cyclicity of 48 in terms of remainder, that is number system, first of all we factorize 2, 4 into 3. 2, 4 is what? In the term of 2, 4 we said 2 raised to power n. The cyclicity is n minus 2, that is 2 square is nothing but 4. The cyclicity of 2 raised to power 4 is 2 square, that is 4. And for the prime, that is 1 less than prime. And is what we want 4 as well as 2. So 2 raised to power 4, that is 16 says we repeat after 4, 3 says we repeat after 2. So I agree with both and I'll say okay Baba, repeat after 4, that is LCM, in which we satisfy 4 as well as 2. Anything repeats after 2 would repeat after 4. So when we have to find the cyclicity of the prime bundles, we find the cyclicity of the individual prime powers and take the LCM. So I am summarizing how to find the cyclicity. When you have prime as a divisor, then the cyclicity is prime minus 1. For the 5, the cyclicity is 4. For the 2, cyclicity is 1. When you have prime raised to power n, 2 raised to power n, this is the special case, then the cyclicity is 2n minus 2, where n is greater than 2, because we cannot get as a 0 or negative value. So, okay, 2 raised to power 1 cyclicity is n minus 2 when n is greater than 2. But what happens when n is equal to 1, that is 2, the cyclicity is 1. When the n is 2, that is 2a squared equal to 4, the cyclicity is 2. For the rest, the cyclicity of 2 raised to power n follow this formula. For other prime raised to power n, the cyclicity is prime raised to power n into 1 minus 1 by p, or the Euler. These two same as the Euler, but this one is different from the Euler. Now, if we have prime bundle P1 and P2, say power is m or n, we find the cyclicity of P1 and P2 with the help of our formula and take the LCM. Say, what is the cyclicity of 100? 100 is nothing but 2a squared into 5a squared. 2a squared, the cyclicity is 2. 5a squared, we can say 5a squared into 4 by 5. It is cancelled out. Cyclicity is 20. So 2 and 20 and is nothing but the LCM is 20. So the cyclicity when 100 divides any number is 20. So we can say the cyclicity of last 2 digit is 20, because remainder by 100 is nothing but the last 2 digit. We find cyclicity with the help of these formulae. When prime, then p minus 1. When p raised to power n, 2 raised to power n, we just divide the Euler by 2. And for the rest, we find the Euler. But if we have prime bundles, we find the cyclicity of the prime bundles and follow the LCM rule. I hope it is clear. Now, the most important thing is how we use cyclicity. The use of cyclicity is not to find remainder, but to reduce power. Please, the only use of cyclicity is to reduce power. When you have 123 raised to power 17 divided by 8, what would be remainder? When you have this type of question, when these two numbers are either co-prime or non-co-prime, first of all we check the number of remainders available for the 8 is how many? That is nothing but the cyclicity. 2 cube is nothing but 2, 3 minus 1, so that we can say 2, 1, that is 2. The number of options available when any number divided by 8, when these two are the co-primes, or we can say even non-co-primes, we'll check the non-co-prime things other in a different way, is nothing but 2. We have only 2 options available. The power is 17 and we have only 2 options available, so we can say this is nothing but 8 into 2 plus 1. We have 8 bundle of options plus 1 extra. This 1 extra is the determination form. This 1 extra is the main thing. We exhausted all options. We left with 1 extra. We can say 123 raised to power 1 divided by 8 should be remainder. The extra works everywhere. And this extra is nothing but the remainder when the power divided by cyclicity. So 123 divided by 8, remainder is nothing but 3. So 123 divided by 17, remainder should be 3. I hope it is clear. I hope it is clear. The question, say, take another question. 127 raised to power 69 divided by 12. What would be remainder? There is nothing common between 127 and 12, so we can directly apply cyclicity. Even there is something common between these two, we can reduce power if possible. The cyclicity of 12 is what? 2a square into 3. 2a square, the cyclicity is 2. 3 is cyclicity is 2 and is the LCM. LCM is nothing but 2. So if you have anything, you just need to know the base should be divided by your divisor and power should be divided by cyclicity. When 127 divided by 12, we have 7 left. Cyclicity of 2 is 2. When this divide 2, we have 1 left, so answer is 7. So the concept of remainder by cyclicity is quite easy. You just need to follow. When number is a raised to power b raised to power c raised to power d raised to power e and divided by, say, a number p where every pairs would be co-prime, then we can say first of all we divide a by p, we divide this one by the cyclicity of this number, we divide c by the cyclicity of this number, we divide this by cyclicity of this number, we divide this by cyclicity of this number, and replacing the powers with the remainders get the answer. Now solve a question. What is the remainder when the 31 raised to power 37 raised to power 39 raised to power 41 divided by 26? See, so we need to divide 31 by 26. The cyclicity of 26 would divide 37. So 26 is nothing but 13 into 2. 13 is prime, so 1 less than 13. 1 for the 2. LCM is 12. So the cyclicity of 26 is 12. So we divide this one by 12. What is the cyclicity of 12 is nothing but 2. We divide 39 by 2 and this one by 1. So we just need to divide dividend by the divisor, the base by the divisor, then cyclicity, then cyclicity, then cyclicity. When we get 1, there is no need to move further. Even the power say 101, no use of 101. Now work on these values. 41 divided by 1, what is the remainder? 0. So replace this power, the first power, replace this power as a 0. 39 divided by 2, remainder is what? 1. 37 divided by 2, remainder is what? 1. 31 divided by 26, remainder is what? 5. So our remainder should be this one. If we solve this value, we will get 5. So the answer for this question is 5. When you have anything a raised to power b raised to power c or anything divided by a number, when we have co-prime bundles, we first base divided by your divisor, then cyclicity. When we reach it at 1, we stop counting the numbers and solve the value. Now solve another question for a better clarity. Now solve one question and we will discuss how we deal cyclicity if we have non-co-prime divisor and dividend. 127 divided by 13 power is say 24. What would be remainder? Here both are co-primes. The cyclicity of 13 we know is 12. So we divide this one by 13 and this one by 12. The remainder 24 divided by 12 is 0. So replace power by 0, that is nothing but the remainder. We replace power always by the remainder when we divide with the cyclicity or divisor. 127 divided by 13, remainder is 10. So 10 raised to power 0 is 1. So our answer is 1. So we can say when the power is multiple of cyclicity, the remainder is 1 when these two are the co-primes. I'm again repeating, why we are taking 0 as in power? Because what I said earlier, we uses all the options available for the remainder. But there is nothing common between 127 and 13. So we say we work with the first power. What we have studied is if you have anything raised to power anything divided by anything, this divided by number and the power divided by cyclicity, if we get remainder 0, write 0. If we get remainder 1, write 1. If we get remainder 2, write 2. If you get remainder 3, write 3 in place of power. If this happens when we work with a co-prime, dividend and divisor. Say take a random question, 122 raised to power 127 divided by 30. What would be the remainder? Someone suggests to you, what is the HCF between 122 and 30? HCF is nothing but 2. Take 2 common from both the values and solve the question. I am saying there is no need to doing all this thing. If you can apply cyclicity, means if you can reduce the power, work on a cyclicity. I would suggest work on a cyclicity. The cyclicity of 30 is nothing but 2 into 3 into 5. Prime 1 less, prime 1 less, prime 1 less. That is the cyclicity is nothing but the LCM is 4. So this power divided by 30 and this power divided by 4. If anything divided by 4, the remainder comes 0, 1, 2, 3. If these two are co-primes, then when we have remainder 0, we write 0. When remainder 1, we write 1. When we have remainder 2, we write 2. When we have remainder 3, we write 3. When these two are the co-primes, but what is common? That is 2 raised to power 1 is common. So we cannot work on a first number. If the common is 2 raised to power 2, we cannot use the first two numbers. But definitely we reduce the power. How? When we cannot work with the first number, so we cannot write 0 as a 0. Then what should we write? We replace 0 as a 1, 2, 3, 4. If you have anything common, just check what is the power. If you have 2 raised to power 1, then you should not use 0 as a 0. If remainder comes 0, instead of 0, 1, 2, 3, 4, we just replace with the cyclicity. If 2 power commons, so instead of writing 1, we should have written 5 if remainder is 1 and so on. What is the remainder here? Here remainder is nothing but 127 divided by 4 is 3. And what is common? 2 raised to power 1. We have problem with the first power only 0. No problem with the third power. So we can work on a cyclicity. 122 divided by 3 remainder is 2. 127 divided by 4 remainder is 3. So our answer is 8 directly. I hope it is clear. I am again solving this question with another example. By 48, what would be remainder? Instead of taking something common or using CRT is one of the best methods. We will discuss CRT and ULS in the coming videos. The cyclicity of 16 I know is 4. How? Because 16 is 16 into 3. 16 is 2 raised to power 4 and 3 is 3 raised to power 1. By the cyclicity formula, 2 raised to power 4, the cyclicity should be 2 square. Prime cyclicity should be 1 less and the LCM is nothing but 4. So by the cyclicity concept, this should be divided by 20, 48 and this should be divided by 4. We divide any number with 4, remainder should be either 0, 1, 2, 3. If anything commons, instead of 0 I will write 1, 2, 3, 4, then 5, then 6, then 7. We just replace. If remainder is 0 we should write 1 if nothing common. If remainder is 0, we write 0 if nothing common between dividend and divisor. If remainder is 1, we write 5 if anything creates problem. If 1 create problem, we write 1 as a 1. So what is the common between 28 and 48? The common is nothing but 2 square, that is 4. So 2 power would create problem. First power create problem, then we should write 0 as a 4. Second power create problem, then 1 as a 5. 127 divided by 4, what is the remainder is 3. It's not creating problem. The problem is only with 0 and 1. The problem with only the first two remainders, 2 raised to power 2. The HCF power is the problem creator of the two remainders, first remainders, and 0 and 1 are the first remainders. The problem is here the remainder is 3, so we do not have any problem. 28 divided by 48 is nothing but 28. 127 divided by 4 remainder is what? 3. 120. So 28 raised to power 3 divided by 48 would be our remainder. Either we do CRT or we can solve it by manual calculation. So we can use cyclicity if anything is common between these two numbers or for the non-core primes. But believe me, the use of cyclicity is just to reduce power. If you are not able to reduce power, we won't use cyclicity. Either we use reverse of the cyclicity or binomial or Chinese remainder theorem. I hope you understand the concept of cyclicity. What we have discussed till date are: first, how to find cyclicity. When we have prime, the cyclicity is prime minus 1. For prime raised to power n, when we have 2n, then the cyclicity is 2n minus 2 when n is greater than 2. When we have 2n, then it is 2n minus 1 when n is equal to 1 or 2. For the rest prime, the cyclicity is p raised to power n into 1 minus 1 by p. For the bundle of prime, says any power or without power, we first find the cyclicity of the primes according to the given formulas. Then we take LCM. If we find the cyclicity, and this is a raised to power b divided by n, base divided by n, power divided by cyclicity. If there is another power, then the cyclicity of this, and we replace the power by the remainders and solve the question. For coprime, if we have anything common between these two numbers, we work like this. We just work what is the common. Say the prime number raised to power 3 is a common, so instead of writing 0, 1, 2, we write 0 as a cyclicity, 1 as a cyclicity plus 1, 2 as a cyclicity plus 2, 3 as a 3, 4 as a 4. If power is 3, in the HCF, we just have to very careful when we are working in a 0, 1, 2 remainders. I hope it is clear. If you have any doubt, feel free to ping me either on Facebook or on this YouTube video thread. Thank you and happy learning.